Hello, I'm Daniel de Almeida Braga, and I'm going to present a joint work between Pierre Fouk, Mohamed Sabt, and me called Dragonblood is Still Leaking, Practical Cache-Based Side Channel in the Wild. Let's start with a little bit of context. Nowadays, we use internet for basically everything, so we need strong and secure wireless protocols allowing to connect to an access point through Wi-Fi. The Wi-Fi Alliance defines some standard protocols to do so, updating them when severe vulnerability appears. Due to recent vulnerabilities on WPA2, the Wi-Fi Alliance standardized WPA3 in early January 2018, which fixed some issues and bring more satisfying security guarantees. Namely, WPA3 is heavily based on a Password Authenticated Key Exchange, or PAKE, called Dragonfly, which brings nice security properties. A PAKE combines the key exchange and authentication parts of the protocol by mixing the password into the exchange. So the knowledge of the password is enough to authenticate the user, and a low entropy password can be used to derive some strong cryptographic material, ensuring the security of the following communications. A key property of such protocol is their resistance to offline dictionary attacks, meaning the only way an attacker can assess the validity of a password is by trying to connect and see if it succeeds. First attacks on WPA3 and Dragonfly's implementations appeared in 2019, named Dragonblood. They targeted various aspects of the protocol, and some of these attacks targeted design flow in Dragonfly, extracting information through what's called the side channel. A side channel attack consists in extracting information by leveraging some implementation particularities. For instance, if we observe this function, we notice that the processing time can be used to distinguish a password containing the letter A from any other password. A little bit more complex side channel allows us to make a clever use of some CPU instruction in order to track the execution of a program and know when some instructions are performed. In this case, if we monitor the long processing function, we can achieve the same result as previously in spite of the constant execution time. So Dragonfly was sensitive to this kind of attacks by design and leaked information on the password, so some heavy mitigation have been added. However, in our work, we show that the current mitigation are not sufficient to prevent cache-based side channel leaks, and in fact, we designed and implemented an attack allowing to recover the password with an offline dictionary attack, breaking the security guarantee of Dragonfly. We designed proof of concept on deployed implementation compiled for production, and namely we targeted IWD, iNet Wireless Daemon, which is an open source Wi-Fi daemon developed by Intel, and FreeRadius, which is a well-known open source radius implementation. Our experiments show that the attack is quite practical and only need a very reasonable amount of measurement in order to succeed. So we really aim to raise awareness on how practical cache attacks can be, in spite of their apparent complexity. So let's discuss our contribution in more detail. First, we exploited a side channel, meaning the information leaks through an implementation particularity. This side channel is cache-based, meaning we're exploiting some microarchitectural properties in order to extract our information. More precisely, we use the well-known flush and reload attack, which consists in flushing an instruction out of the CPU cache and see how much time it takes to reload it. If the victim tried to execute the instruction in the meantime, the access will be quick since the victim got it back in the CPU cache to execute it. Otherwise, the reloading process needs to go look for it in upper memory level, which will take a little bit more time. To increase our leak, we also use the performance degradation attack, which basically consists in constantly flushing some instruction out of the CPU cache in order to make it longer for the victim to execute. But we will get back on how this attack were combined a little bit later. Coming back to our contribution, the attack targets the password conversion, since in Dragonfly, one of the first steps is to convert the password and the identity of the peers into a point on an elliptic curve. And finally, we end up with a dictionary attack, allowing the attacker to simply gather information and perform the computation offline, possibly with high computational power. Regarding the Dragonfly protocol itself, the workflow is quite classical for a PAKE. We convert the password to a usable form and use it to authenticate the key exchange. The only unusual operation consists in the password conversion method. Indeed, various methods exist, but they choose to use a try and increment approach. Basically, we feed the password the peer's identity A and B, which will be the MAC addresses for WPA3, and a counter to a key derivation function, and check if the output is a valid X coordinate on a chosen elliptic curve. If not, we simply increase the counter by 1 and start again. To avoid any obvious leak through the running time execution, an additional parameter k is used as a minimal iteration number to be sure the number of iterations does not depend on the password's value. So if this mitigation makes the overall execution time constant, the control flow is not. And using the flush and reload attack, we are able to monitor this instruction to distinguish one iteration from another. With the same technique, we monitor line 6, allowing to guess exactly at which iteration the password has been successfully converted. So this works in an ideal scenario without optimization and system noise, but in practice, we had to degrade the performance of the check performed line 4 in order to achieve a high accuracy and successfully mount this attack in a real-world scenario. At the end, the attacker is able to know, for peers A and B, exactly how many iterations the secret password needs to be converted into a point. So remember that changing either A or B may change the number of required iterations, since they are both involved in the X coordinate generation. From there, the attacker can perform its offline dictionary attack. So, assuming the attacker found that for A and B, the password needs 3 iterations to be converted. He can convert every password from a dictionary using the same method and only keep the password needing the exact same amount of iteration. Then, from the remaining password, the same process can be performed to further reduce the dictionary by changing the identity of one peer until the list is small enough to be tested or until only one password is left. Now that we have seen how the attack works, let's see how an attacker can actually set it up. So let's assume a user, which would be our victim, is connecting to the access point through Wi-Fi, and the goal of the attacker is to steal the Wi-Fi password. We will assume that the attacker has a non-privileged spy daemon deployed on the victim station, which will monitor some behavior on the Wi-Fi daemon. So this spyware can be embedded as a malicious attachment or simply be part of a software our victim is using. In fact, the piece of code is quite small and do not need any special privilege. We'll also assume that the attacker is within network range, so he can deploy a fake access point and trick the user into connecting to it. So the Wi-Fi daemon will use the password to connect. We need a rogue access point so the attacker can change the MAC address in order to gain new information about the password every time the user tries to connect. In this context, and assuming our hypotheses are met, we have a spy process on the victim and a rogue access point. Now, every time the victim tries to connect to the access point, the spy will generate an execution trace, which can be parsed and interpreted to extract exploitable information about the password. In our case, this information is the number of iterations needed to convert the password into a point. Using this information, the attacker can perform the offline dictionary attack and eliminate all passwords which do not meet the criteria defined by the leaked information. So the more information we gain, the less possible password remains. And except for the spying part, all this attack can be performed fully offline. Cache-based side channel tends to need lots of measurements in order to be reliable, because leaks are often quite small and some system noise may interfere with our measurements. However, by combining the flush and reload attack and the performance degradation attack, we are able to achieve a 99% accuracy with only 10 measurements per MAC address, while the original Dragonblood attack needed twice more measurements to gather less information. The overall complexity of this attack is defined by the size of the dictionary we consider, because if we have more passwords to eliminate, we'll need more information about the secret password. But as you can see, the number of traces required to eliminate all wrong passwords from a dictionary is only doubled when we increase the dictionary size by a factor of 10 to the power 7. And for instance, the Have I Been Pwned dictionary gathers passwords revealed in previous database leaks. And it only needs an average of 20 traces to eliminate all wrong passwords. So to give you a rough idea of the cost, since the offline search is fully parallelizable, exploiting AWS instances allows to perform this search in less than a second for a negligible cost. So, of course, we disclosed this vulnerability to the concerned project before publishing any results, and both Intel and FreeRadius were very responsive, so we designed a patch for both implementation and integrated it into their code base by committing to the project. So this vulnerability is fixed from IWD version 1.9 and will be fixed in the next FreeRadius release. Thank you very much for your attention. If you have any question or if you want to discuss about this, feel free to reach out and to take a look at our proof of concept. Goodbye.